Welcome to Chemistry 112. We're going to continue where we left off, but we'll start with a little bit of a real quick kind of review, just to kind of remind us what all's going on. Another quick reminder, Group 2 should be meeting in lab this week. The Group 2, so we should be doing, I do believe the kinetics lab. So now come in, be ready for that. If anyone needs to make up a lab from Group 1, they're more than welcome to show up. Otherwise, we'll be doing Group 2, the kinetics lab. So quick reminder, I'm going to jump to the doc cam before we get started. We have introduced a few concepts over the last two chapters. We've introduced the basic acid bases and the relationship that H plus, if we take the negative log of base 10 of that, would give us the pH. The negative log of OH minus would give us the POH. And to get backwards, you would say, what, 10 to the negative pH would give us our concentration of H plus. And we can relate all these things to the KW. 10 to the negative 14th equals H plus and OH minus. Then we introduced weak acids. Weak acids, which when we set up the equation, we said Ka equals the concentration of acid over H plus times A minus. And because there was no amount of acid or base present, there was no amount of protons or conjugate base present, we set those as X because we did the ice table and it became Ka equals X squared over HA. And because we typically knew both of these, we could say Ka times HA. And we square rooted that to give you the concentration of acid. And then that could be plugged into there. So all that was last chapter. This chapter, we started off just the week before spring break introducing buffers, which now suddenly we have some amount of conjugate base and some amount of acid, but we don't know this quantity. So no longer are these two quantities equal. And so often we separated this to say the concentration of acid equals Ka times HA all over A minus. However, we rearrange that to give us pH equals the pKa plus log of A minus over HA. And that was our buffer equation. That if you find the pKa, then you can modify it slightly depending on whether there is more acid or base. More acid than base is going to lower the pH. More base than acid is going to raise the pH, but not by too much. And the hard fast rule is that buffers typically only work within plus or minus 1 pH unit of the pKa. But that's where we finished off on the Thursday before last. So I just wanted a quick reminder of the various equations we have seen before we go on, because this next part is all about titration, the act of adding acid to base and seeing what's going to happen. We're going to see all these situations. We're going to need this equation. We're going to need, depending on whether we have a weak acid or not, we're going to have that equation. When we have a weak acid, we're going to have regions where we call the buffering region, where we're going to need that equation. It's going to require us to think through all of our faculties to get through this. So we'll try to go slow, take our time, but go ahead and get started. So titration of acids and bases can be analyzed either graphically or mathematically. I will focus largely on tests on the graphic analysis because, well, that's so much easier. But mathematically, we can do all the math on what we're actually seeing graphically. In fact, that's how I've often generated many of these graphs that we've used on the test. I use a mathematical representation to graph this out. In General Chemistry 1, we typically only looked at one data point. That one data point was the equivalence point, the point where there's equal amount of acid and base. And that's when the neutralization occurs. We usually use the colorimetric titration to show when this has happened, when it switched from, say, clear to pink. We said, oh, it went from acidic to basic, so we must have crossed through that perfect median point where acid and base equal. Now, when we do this mathematically, we're going to need ice tables, we're going to need Ka expressions, we'll need to even calculate for dilutions, because when you add acid to base, you're going to be adding volume 1 to volume 2. And the total volume is going to change throughout. Now, the ice table that we've done typically uses moles of reactants and products rather than molarity. However, we didn't, up until now, it didn't really matter, and we didn't really care because the volume never changed. The volume never changed. Thus, the molarity never changed. So when we subtracted products from reactants, it's all out of the same initial volume, the same final volume. So we didn't have to turn molarity into moles or moles back into molarity. However, when we calculate the molarity of acid and the molarity of base, we're going to need to turn them into moles, because depending on how much volume we have, depends on how many moles we get added, and thus how many moles actually subtract. So it's something we'll take into account as we do some of these math problems. Okay. So the first thing is looking at a titration curve graphically. What we see here on the right is both a strong acid with a strong base. So a strong base is added to a strong acid. And then on the bottom, a strong acid is added to a strong base. Now, what we see here is a very, very low on the top one, a very, very low pH. As we add the base, the pH changes a little, but not very much. It goes from essentially 0 to maybe like pH 1.5, maybe 2. And then we see a very sharp increase. And the equivalence point, which is halfway between this region and this region, is right at pH 7. That's one of the things about a strong acid, strong base scenario. When the acid and base are completely neutralized, we get a neutral pH, pH 7. Then it slowly climbs up to 14 after it has that really sharp increase. Mathematically, we could look at the integral, not the integral, the derivative of this, and then the second derivative. And basically the second derivative of this, you could find this region as essentially it goes to, the second derivative goes to 0. This is what's known as an inflection point. The point where essentially acceleration and then rapid deceleration, and then it's actually going negative again. So we go from positive to negative, and it hits 0 right here. So you can usually see it by eye, but if you want to be really accurate, you can do a mathematical approach to this. But one of the key things here is that the pH starts either really low or really high. It doesn't change very much until it hits the equivalence point, and the equivalence point happens at pH 7. These are typical strong acid, strong base. Where the pH starts depends on where the concentration of the original acid is. For example, if it's 1 molar, it's going to start right there. If it's 0.1 molar, it'd probably start at pH 1. If it's 0.01 molar, they'd start at pH 2. So it depends on the concentration of the acid, but it should start really low because a strong acid is a strong electrolyte which completely dissociates. Now, when we calculate for this, generally there are 4 regions that we can treat here. One is the prior to titration, which is the easiest one. We've done this a dozen times before. Prior to titration is just acid, no base. We don't have to do anything. Second region is somewhere during the titration. So where it's still more acid than base or more base than acid, we can do that. Equivalence point is really easy for a strong acid, strong base. And then after equivalence point. These are the 4 points that we can treat separately in each a different way for both strong acids and weak acids. But we're going to need ice tables to help with this. So when we treat the initial pH prior to titration, if it's just acid and no base is added, strong acid completely dissociates. All we have to do is take the negative log. Because there's no base, we don't have to change the molarity. It's just negative log, and that gives us our pH. However, once we start adding the base, now we have to use an ice table, and we're going to have to break it down into these 4 steps. Step 1 is calculate moles of both acid and base. Take the molarity and the volume to give us moles. Use the ice table to cancel out some acid with the base. Step 3, which is dilute, turn moles back into molarity. So you have to use the VA of the acid and the VB of the base to calculate a V total. And then 4 is just then the negative log again. The brilliant part is at equivalence point, pH is just 7. For a strong acid, strong acid, pH is just 7. If you did step 1 and step 2, step 1 was we turn molarity into moles. Step 2 is you use the ice table to cancel out. Well, at equivalence point, the acid and the base cancel each other out, and you get a concentration of acid is 0. The concentration of base is 0. So you wouldn't take the negative log of 0. You'd remember that you're perfectly neutral. When there's no acid and no base, we just worry about the water's natural acidity, which is 10 to the negative 7th. And so negative log of 10 to the negative 7th is 7. Now for the pH after equivalence point, step 1 and step 2 are the same. The only difference is that there's going to be more base than acid, and so the acid will completely go to 0, and there will be base left. Then we will calculate the actual OH molarity, and then we'll calculate POH and turn it to pH, just to keep it on the same scale. So I'm going to write some numbers down, and we're going to work through hypothetically these numbers. If I have 25 milliliters of HCl, and I have 0.30 molar NaOH, and I say there's 13 mils to get to equivalence point. So then I ask, calculate the pH at 0, 5, 13, and 15. 0, 5, 13, and 15. Now you notice I haven't given you the molarity of the acid. However, we can calculate that with relative ease. We have to remember back to general chemistry. MaVa equals MbVb at equivalence point. Mb, 0.30. The volume of base needed, 13 mils. The volume of acid is 25 mils. So what is the molarity of acid under those situations? No, I need to. So what is the molarity of acid under those situations? So 0.3 times 13 divided by 25. The molarity of acid would be 0.156. Okay. So step one, the 0.1, where it's just 0 mils. 0 mils of base means we just take negative log of the amount of acid, 0.156. Negative log base 10. 6, and that would give us a pH of 0.807. 807. Now, step 2. Here's where it gets here's where they actually are hard. And I'm not going to lie and say, oh, this is usually no. So for our ICE table, I'm going to write ICE. We have essentially acid, we have base. We're going to just try to cancel these guys out. So with 25 mils times 0.156, that's going to be our acid. 25 times 0.156 gives us 3.9. Now we use 5 mils of the base times 0.3. Times 0.3 is 1.5. So we have 3.9 millimoles of acid and 1.5 millimoles of base. We're going to subtract away 1.5 millimoles of each one till we have 0 millimoles of base and thus 2.4 millimoles of acid. So there's our moles of acid remaining. Then we have to redilute. So we have 25 mils. How much base did we add? We added 5 mils of base. When we added 5 mils of base, it went to 30 mils. So 2.4 divided by 30 means our molarity has gone to 0.080 molar. So we've gone from 0.156 to 0.08. Then we take negative log of 0.080, and that would give us our pH. Our pH has gone from 0.807 to 1.09. Oh, 1.0. I'll round it to 1.10. 1.10. Now, because this is a strong acid, we don't actually have to do the third one. We could, but essentially what you would have is ICE. Here's your acid. Here's your base. You would have said, okay, this is 3.9. This is also 3.9. Minus 3.9, minus 3.9. You get 0, you get 0. So this is just pH 7. So we don't actually have to do that one. But point 4, the fourth point, so we do it one more time. ICE. The beauty of this is the amount of acid we've added will not change. That will stay at 3.9 each time because the initial amount of acid, we're not adding anything more there. We're only adding more base. So 15 mils times 0.30, what is the moles of base? 0.3. Means this is jumped up to 4.5. There's no longer more acid than base. Now there's more base than acid. So we're going to subtract out our acid. So we have 0 millimoles of acid and we have 0.6 millimoles of base. Part of the next thing is we have to calculate the molarity. So we had 25 mils of acid and we added 15 mils of base. 25 plus 15 is equal to 40 mils. So 0.06 divided by 40. The molarity of base, this is 0.0015 molar OH minus. Now remember, we can do a negative log of this number as is, but this will not give us pH. This will give us POH. So we have to take this with a grain of salt. So this, we get a POH of 2.82. So our graph doesn't look like this. It doesn't look like, let's see, 0 point would be what, at 0.8, then at 5, going up to 1.1, and then at 13 jumps up to 7, and it doesn't jump back down to 2. It doesn't jump back down to 2. No, it keeps going. It keeps going and levels off again. So to get pH, pH is equal to 14 minus POH. So we'd have 11.18 pH. So what are 3 points? Well, at our 4 points. At 0, 5, 13, and 15. We have 0.8. 0.8, we'll say 0.81. We have 1.10. We have 7. We have 11.18. That's how big a jump is. It doesn't move by much until it gets really close to the equivalence point, then it jumps up super high and shoots past it. 2 mils past the equivalence point, and we're already at 11.18. And it would keep going up as we add more and more base. Let's go back to the pump. Okay. Doing this again. This time I'm adding an acid to a strong base. If I have 15 mils of NaOH, I titrate it with 0.75 molar HI, and it's a 10 mils neutralize at EQ UIV. There's a pH at 0, 5, 10, and 15. Pretty evenly spaced. Pretty evenly spaced. Step one, once again, is to what is the molarity of base? MA, VA equals MB, VB. So we have 0.75 molar. We have 10 mils. We have 15 mils. So the molarity of base is 0.5. So molarity of base is 0.5 molar. Okay. Point one, where there's 0 acid added. The negative log of 0.5 would give us our POH. Give us our POH, which is let's say 30. So 14 minus 0.30, because I'm asking for pH and not POH, is 13.70. That's our first point. Our second point, we're going to do our ICE table, ICE. It doesn't really matter which one you put first, which one you put second. The amount of base we have is going to be 7.5. That's not going to change, but the amount of acid will. Now, because 5 is half of 10, I can tell you right there, half of 7.5 is what? 3.75. 3.75. When I subtract out 3.75, both sides, I'm going to get 3.75 and 0 amount of acid. Last step is I got to calculate for my dilution. 3.75, we have to add our 15 mils to our 5 mils of acid. So 3.75 divided by 20 is 0.1875. Now, technically, I shouldn't have that many sig figs, but we'll leave them for now. So it went from 0.5 to 0.1875. Adding half of the amount of acid, half the amount of acid to the base as we needed, we only dropped from 0.5 to 0.1875. It's not a huge, I mean, it is a big drop, but it's not as big a drop as you would expect to say half neutralize the base. So we take the negative log of 0.1875. That would give us our POH because we're still in the base. That drops it down to 0. We'll say 73, and then 14 minus 0.73 drops it to 13 point what? 27. So we went from 13.7 to 13.27, and we're half neutralized. I want you to realize half neutralized, and it's only dropped by just over, well, not even a whole, not even half a pH unit. We've gone from zero acid to half equivalent's worth of acid, half neutralized. At equivalence point, I can skip the math and just say pH 7 because strong acid, strong base, perfectly neutralize. Don't have to worry about it. But after the equivalence point, we have to do the math. So AH plus, OH minus. OH minus isn't going to change. OH minus, we still have 7.5 because that's what we originally started with. But when we add 15 mils, we have 7.5 plus 3.75, you get 11 and a quarter. 11.25. So when we subtract out our base, should get 3.75 again. But now, that's 3.75 acid. This is convenient because we've been working only in factors of 5. That's why I'm able to do this so quickly, because I'm taking 0, 5, 10, 15. If it was like I took 0 mils, 3 mils, 8 mils, 12 mils, it would be a lot bigger pain in the butt. I'd have to do all the math. But we're able to shortchange this a bit. So 3.75 millimoles of acid, our new volume. So we took, let's see, 15 mils of base, and we added 15 mils of acid. So the new volume is 30. So I take 3.75 divided by 30 now. So we have 0.125 molar H plus. And because now we're in the acid region, negative log of 0.125. 25. It's just going to be pH 0.9. 0.90. So just to reiterate, trying to draw a graph real quick. Okay. If that's 5, 10, 15. If that's 14, that's 7. We started like, and then I mean, it's really not much of a change till we get really close, and then we go, and then shoots all the way down, and then not much of a change after that. That is the nature of strong acids, strong bases. We don't see a huge change in pH until we get really close to the equivalence point, and then it changes very much so drastically. Just looking at those 4 data points. Yes, we could calculate more data points. I'm not going to make you calculate more data points, but it would simply be the same thing. I could have done, instead of 10, I could add 11 in there. See what point this would be. We could figure out that. Wouldn't be hard, considering all we've already done. So pH 7 and 0.9. Now, weak acids and weak bases are a completely another beast. Those are ones that are a pain in the butt to calculate, but they are incredibly useful when you're graphing, when you're looking at a graph. They're way easier to tell that it's a weak acid or weak base than a strong acid, strong base, because it has a couple key features you can look for. You'll note that we have a weak acid titrated with a strong base and a weak base titrated with strong acid. One, the pH starts quite a bit higher, So instead of starting around 0, the pH here starts around, like, say, 3. You see in here, it increases by a couple pH units, and then it levels off for a slower build until we see that inflection point. So it's more of a gradual increase rather than the sharp increase. This region here, this middle region where it's kind of after it picks up and then slows down, is called the buffering region. That's the region where, remember, the buffer should work. That within plus or minus 1 pH unit of the pKa, it's essentially preventing a large increase from occurring. You'll notice another thing. The equivalence point, which is the inflection point, occurs not at pH 7, but actually above pH 7. Because what's going to happen is that when all the acid is neutralized and base is formed, we have a lot of conjugate base. The conjugate base can then undergo a reverse reaction. The reverse reaction of conjugate base is that the base attacks water to produce the conjugate base, the A minus attacks water to produce some HA and some hydroxide, meaning that when the HA and the OH minus have canceled out, we are going to produce some small amount of OH minus, meaning the pH will be slightly above neutral. And with a base, it'll do just the opposite. A weak base, when we have the conjugate acid will attack water and produce acid. So you'd have a pH below 7 at equivalence point. But being able to recognize this is a good thing. Why? It's because of a key point in this graph. You cannot do this with strong acids and strong bases. I reiterate, you cannot do this with strong acids and strong bases. You can do this with weak acids and weak bases. So what you have to do is you have to be able to recognize this is a weak acid titration or weak base titration. And that is the region we want to look at is called the half equivalence point. It's a kind of weird term, but if you know what the equivalence point is, which is the point where acid and base neutralize, the half equivalence point is literally half of that volume. Those last two problems, the first one, the equivalence point was at 13. Half of 13 would have been 6.5. So 6.5 mils would have been the half equivalence point. The last problem we did, 10 mils was the equivalence point, so the half equivalence point was 5 mils. In these questions, 25 mils are needed to neutralize that. The half equivalence point would be exactly 12.5 mils. The idea here is that when you're at half equivalence point, half of the acid has been neutralized to produce an equal amount of conjugate base. Half of the acid has been neutralized to produce an equal amount of conjugate base. And going to the doc cam real quick, we can see that, we'll see that what happens if pH equals pKa plus log of A minus over HA. If A minus equals HA, you get this whole term cancels out to be log of 1. Log of 1 equals 0. So what happens is when these two are equal, this whole term drops out and you're left at half equivalence point, pH equals pKa. And what does that mean in terms of us is that if you have an unknown acid, but you have several different possibilities, by titrating this and measuring the pH at equivalence point and the pH at half equivalence point, you can figure out what the pKa of that acid is, or what the pKb of that base is. And thus, you can actually determine what is that acid. Is this acetic acid? Is this boric acid? Is this ammonium? What is it? We can figure that out by actually doing this titration. It actually makes our life a whole heck of a lot easier. That's one way to determine the identity of an unknown acid, as long as it's weak. If it's strong, who knows? It could be anything. It could be HI, it could be HCl, it could be HBr, it could be HNO3. There's other ways to figure it out, but titration-wise, we cannot tell. So because of the nature of a weak acid, weak base, these steps are a little bit harder. We still have to do the negative log. But we also have to do the calculate the amount of H plus. The amount of H plus is not simply the amount of HA, the strong acid. So remember a couple pages ago, we said in order to calculate the amount of HA of an acid, we had to take the square root of Ka times HA. So at the initial point, we have to do this step because of this setup. pH prior to the equivalence point, we still have to do on the prior to equivalence point, we still have price table. But however, now we have to calculate for the amount of A minus formed. And then we can instead of doing the redilution, you can say pH equals pKa log A minus over HA. Does this still use molarity? Yes. Do you have to calculate those for molarity? No, because they're both in the same volume. If you want to calculate it for molarity, you can. It isn't as important. At equivalence point, once again, it's not quite so easy. At equivalence point, we have suddenly, instead of just being pH 7, we have all A minus left. So you have to calculate how much A minus would be left. You have to calculate, well, if all the HA has been turned into A minus, we have to say HA times VA over V total. So to figure out how much A minus is left, the molarity of that. We have to calculate the KB because now we're dealing with a basic situation. And then we're going to calculate the pH the same way as we did at the initial point, except now it's the POH. So you're turning it back into pH. And then after equivalence point, if we're titrating with a strong base, here's the beauty of it. Strong base, strong acids and strong base dominate. If you had a strong acid and a weak acid in solution, the strong acid reacts completely before the weak acid. If you have a strong base and a weak base in solution, the strong base reacts completely before the weak base does. So once we get past the equivalence point and it's just strong, we can treat it like it's just a strong. You don't have to use Ka, Kb, all that stuff, because if it's just straight up OH. So we got to do a little bit more work here. 25 mils of acetic acid. I'm going to just go ahead and give you the 0.156 molar. And we're going to say 0.30 molar of NaOH. And we don't really, I just want the same values just to compare, from problem 1, 0, 5, 13, 15. I use the exact same concentrations. The only difference is that now we have a Ka to worry about. Quick reminder for this one. We had 0.807, we had 1.1, we had 7, and we had 11.18. Those were our pHs. Now, at 0, it's just a weak acid. So the amount of H plus is equal to the square root of our Ka times our Ha. H plus is the square root of Ka, which is 1.8 times 10 to the negative fifth times our Ha, which is 0.156. So the amount of H plus is just going to be 0.0016, we'll say 76. The negative log of that, the log of this number, 76, is going to be 2.78. So right now, look at the difference. Instead of 0.81, we have 2.78. Already a good deal, like almost 2 full pH units higher. Now at 5 mils. So we're going to write HA, OH minus, and on the other side we have A minus. We're going to start with 0 amounts of that. 0.156 times 25, well, that was 3.9. We said 5 mils times 0.3 molar was 1.5. So I see. When we subtracted out our base, we added that amount to the A minus on the other side. So 1.15, and that became what? 2.4. Now to get the pH, we can say pH equals pKa plus log of 1.5 over 2.4. Well, the pKa is just the negative log of Ka. 0.8 times 10 root negative 5, which is 4.74. So 4.74 plus that, plus log of 1.5 divided by 2.4. This is the buffering region. We add that. This ends up being just negative 0.2. So this buffering region is 4.54. So comparing this. The first point was 0.81 versus 2.78. Second point was 1.10 versus 4.54. We see a large jump. Could be larger, but large jump. 0.3 at equivalence point. 3.9 HAICE. OH minus is 3.9. The A minus is 0. If I have minus 3.9 minus 3.9, it goes to 0. That goes to 0, but that becomes plus 3.9. So 3.9 millimoles of A minus. Well, what's our new volume? Got to remember we used 25 mils of acid and 13 mils of base. So the total volume is 38. 3.9 divided by 38 is 0.10, we'll say 3 of A minus. Now, why is that important? Because this reaction, A minus plus water, goes reversibly to HA plus OH minus. Setting up this equation, KB equals HA times OH minus over A minus, which becomes KB equals X squared over A minus. That should look somewhat familiar. So to calculate OH minus, we're going to take the square root of KB times our A minus. How do we get our KB from our KA? KB is going to be 10 to the negative 14th all over Ka, which is 1.8 e to the negative 5th. So we have 10 to the negative 14th divided by 1.8, 10 to the negative 5th. So we got a KB of 5.56 times 10 to the negative 10th. 10 to the negative 10th. So plugging that in, square root 5.56, 10 negative 10 times 0.103. 103. So we get the concentration of base. The concentration of base to be 0.000007, we'll say 57. Take the negative log of that, and we get the negative log of that. We get POH is 5.12. So pH is equal to 14 minus that, minus 5.12. And so we get a pH of 8.88. Comparing that to our original concentration, at equivalence point, we had a pH of 7. Yeah. Could have told me when I forget. Oh, we had an original pH of 8 point. We had a pH of 7 at equivalence point. Now we have a pH of 8.88. So what I did, I converted it all into A minus. I diluted. I set up my expression. I had to find my KB. I found my OH minus, found my POH, I converted it into pH. And the last step, which is just going to be the strong base portion, we'll do it, but just to show you, it's actually going to be the same as if we did the strong acid, strong base. HA, OH minus, A minus. Well, that's 0. We said if it's 15 mils and it's 0.3, said, oh, that's 4.5. And that becomes 0.6, 3.9. But because we have straight up naked base left in solution. 0.6 divided by, let's see, we said 15 plus 25, which is 40. 40. We had 0.015 molar base. The negative log of that was 1.82. And then 14 minus 1.82. Oh, I must have screwed up the last one. I must 12.18. Let's see. Six. Oh, I see what I did. Whoopsies. Whoopsies. Last one I added an extra 0 when I did that. So I did a 0.06 instead of 0.6. Oh well. 12.18. So once we neutralize all the weak acid and we have an excess base, you treat it as a strong base. When there's weak acid remaining, weak acid takes precedence. But when there's strong base left over, the strong base overwhelms everything else. As I said, I will probably not ask you, I might ask you a strong acid, strong base question on the test. Probably not a weak acid, weak base, but it is incredibly good practice. If you can do this, you can do anything. This is probably the hardest thing all semester. All right, the hardest thing all semester. If you can do this, you can do anything. Now, I'm going to probably finish up with polyprotics and not go into the KSP till Thursday. But polyprotic acids. There are some acids that have more than one proton. There's three of them that really come to mind. Carbonic acid, which is H2CO3, sulfuric acid, which is H2SO4, and phosphoric acid, which is H3PO4. Are there others? Yeah. Are they common? Not really. But these guys have multiple protons that can be lost. Unlike a dihydroxo base, these guys lose their protons, one proton at a time. Meaning, all the atoms will lose proton number 1 before any of the atoms will start to lose proton number 2. And for that reason, we're going to see 2 equivalence points or 3 equivalence points depending on how many protons can be lost. How many protons can be lost? And the equivalence points should be approximately double and triple each other depending on how many protons. So if it took 25 mils to remove all of the first proton, it will take 50 mils to remove all of the second proton. And another thing to note is the half equivalence points if they are weak acids. If they are weak acids, the half equivalence points for each situation will be equal to the pKa1 and the pKa2. So if this is carbonic acid, the pH at 10 to the negative at 12.5 mils would be the pKa1. And the pH at which would be like 37.5 mils would be pKa2. So halfway between 25 and 50 would be pKa 2. However, if the first equivalence point is from a strong acid, which is sulfuric acid, you cannot find the pKa. There is no pKa for a strong acid. Because remember that the Ka for strong acid is said to be over 1,000 or like at least over 100. So we're talking about 10 to the a negative log of that would be like you would be looking at a negative pH, and we're not seeing that. Because the easiest thing to do is solve a titration problem using a graph. Expect at least one, if not 2 or 3 problems involving solving a titration problem using a graph. This is so much easier to do because a whole hell of a lot less math. Step 1, it's determine whether this is acidic or basic to start. What is being added to what? 2, determine the pH at equivalence point. To find out whether it's a strong acid, strong base, or weak acid, strong base, or a weak base, strong acid. So if it's at pH 7 at equivalence point, then it's strong, strong. If it's less than 7 at equivalence point, it would be a weak base. And if it's greater than 7, it's a weak acid. From there, regardless of whether it's strong or weak, we want to figure out the concentrations of everything involved. Typically, you'll be given one concentration and you won't be given the other. So you'll be using that graph to find the concentration of the other. So what will you need? You'll need the volume of acid and the volume of base. One of those will be given. The other, you'll look at the graph and you'll say, oh, that's the equivalence point. That's all I need to do. But step 3 is the hard part. You have to remember, if it's weak, what's the pKa? If it's strong, there is no pKa you can find. But if it's weak, what's the pKa? And of course, if it's polyprotic, find out what's the second or third pKa, but that's less common. But okay, so don't get add happy if don't think you can always get the pKa. This case, okay, I'm titrating 25 mils of acid with 0.75 molar base. So we have 25 mils for acid, and we don't know the HA. And we have 0.75 molar base. Now, I don't have the concentration, the volume of base, but we look, where does the equivalence point happen? It happens about 20 mils. This is about the jump where we see it. So we have volume of base is 20 mils. Now, before I go any further, is this weak or strong acid? So we look. Here's pH 7. Where's about the middle of this? The middle of this is about, well, it's basic. pH 9, pH 10, 9.5. It's definitely basic. So what does that mean? It's weak. Another hint would be this sharp uptick right there, followed by the gradual growing up. But so what does that mean? Before I switch to the doc cam, what is the half equivalence point? Well, half of 20 is 10. The pH at 10 is a little over 4. Maybe we'll say 4.1. So pH at half equivalence point is 4.1. So pKa is approximately 4.1. On a question like this, am I expecting you to get it exact? No, get it close. get it within a standard a significant figure. But so what else can we determine? We go, what is the concentration of acid? MaVa equals MbVb. 0.75 times 20 equals 25 times unknown. So we say 0.75 times 20 divided by 25 would give us the molarity of acid is 0.6, which is this times this divided by that. Times this divided by that. So those are the two things you can find. Initial concentration of acid and the pKa. All you need to find. A lot easier to do. A lot shorter steps. You can find them. Remember, just molarity times volume equals molarity times volume. pKa, you have to find the half equivalence point. And let's see. Do I have one more? If I want the actual Ka, you would then take the 10 to the negative, whatever it is. So 4.1, 4.2. You get something to the 10 to the negative fifth. Okay, we will not do that. We will not start there. But the last major topic of this chapter, which we'll get to, is KSP. KSP is the solubility product. It is the predicting how much something will dissolve in solution. Specifically, it is often used for insoluble salts. Those precipitation reactions we often used in General Chemistry 1, when we said, oh, if I mix silver and chloride, I would get silver chloride solid that forms in solution. If I did barium not barium hydroxide, but if I mixed iron and hydroxide, I'd form iron hydroxide. And you can predict how much these guys will dissolve based on a K expression. And so that will be the last major topic we will discuss of this chapter. And then we'll start looking at some of the review problems. However, come test time, I'm going to do something a little different. This may be for your benefit, maybe not. I don't know. But we're going to do maybe not perfectly in class, but I'd like to do like an evening exam like I used to do. It'll be mostly multiple choice. So there's not a lot of show your work kind of things. So that might benefit some of you, but it'll also be, you don't have the whole week all set. We'll try to figure out a set time to do that. If you can't make it that time, I ask you set something up in advance with me, either like the day of, the day before, or the day after, but we got to knock that out. So we got to figure out, set up maybe a survey monkey thing, figure out the best day to maybe do that and get most of you in here and take it at that time. But that's where I'm probably going to be shooting for this test, possibly the next test. But okay, with that in mind, I thank you. Have a good day. I will talk to you in lab for a good deal.